That is our open source software for solving POMDPs. The work I present here is of my advisors, David Su and B. Sandy, and several other students and collaborators. Right, so consider a problem of a robot vehicle that has to navigate a crowded area with lots of people around. So this is the real world. It is highly dynamic, the sensors are noisy, so it involves lots of uncertainty. What's even more worse that we have to make decisions in real time. So now this is the POMDP, types of POMDP problems that we are interested in, and this is the complexity that we are trying to deal with. So after this talk, I hope you will learn two things. One is a key idea behind our algorithm, DESPOT, and how it can make POMDP planning tractable. Secondly, I will talk about the APPL Toolkit and how you can use it to solve your own problems. Alright, so very briefly about POMDP models. I will just introduce them through a simple example of a robot navigation problem. You have this robot in blue here that has to avoid these red obstacles and has to go to this target location. Now this robot has states, its location. It has a set of actions, moving around in a direction, and it receives some observation from the environment. That is in case a local patch of this map. So this word is noisy, so that we will represent the transition function in this problem as a probability distribution, and similarly our observation function is also a probability distribution, so it has the probability of receiving an observation after taking action in a state. Finally, we have a reward function that basically informs the objective of the task. Now in the POMDPs, the state of the agent is not known. We can only infer it from a sequence of observations. What we do know is only a belief, a probability distribution over the state. Now again, these beliefs, a policy, now is going to tell us what action to take given a belief, a probability distribution. Okay. So the way a policy in a POMDP is executed is that we start from some initial belief. Our policy defines what action to take. So we take the action and we receive some observation. Now given that observation, the previous action, and the previous belief, we are going to update our belief. Right? And then given that next belief, our policy again determines actions and so on. Alright, so the question, how can we do planning in POMDPs under uncertainty when we don't know what state we are in? So actually, this can be formulated as a search problem in a graph, but this graph is in the space of beliefs. So each node of this graph, these big circles, represent a belief that is a probability distribution over states. Now, we are going to represent all actions that the robot can take by edges, and then all observations that we may receive after taking action at other set of edges. So starting from a belief, we take an action, receive an observation, and we end up in a new belief. Alright, so we can just do kind of standard search in this graph, and we can use dynamic programming in balance equation. So in the balance equation here, this max operator corresponds to choosing a branch in the belief tree. And then the thing that we are maximizing is the immediate reward and the expected future reward. Now in this case, because we don't know what observation we may receive in the future, so that we have to take expectation over observations. Alright, so things are quite straightforward. Now we have a tree, we can do search, so what is so difficult about this? So the difficulty comes with the size of this belief tree. Okay, so there are two curses that determine the size of this belief tree. First is the curse of dimensionality. So large state spaces are well-known difficulty for all planning problems. That basically is the number of states is exponential in the number of state variables, or dimensionality of the state space. But here is even worse, because we have beliefs now. So in the next representation, beliefs, the size of the belief space is exponential in the number of states. So now we have a second curse, the curse of history, that corresponds to long planning horizon. So So how long we have to look into the future to decide on actions. And in the belief tree, this corresponds to the depth of this tree. So that you can easily see that the size of this tree is going to be exponential in the depth, so in the planning horizon, and the basis of both the number of actions and the number of observations, basically because of this branching. So yeah, this is a problem. And now I will tell you what is our ID that can make this search tractable. So our ID is quite simple. Is basically we are going to represent uncertainty by sampling future scenarios. So by sampling states, we are going to alleviate the curse of dimensionality. By sampling observations, we are going to alleviate the curse of history. By this, we will be able to reduce the size of this belief tree, and it's going to we are getting rid of the exponential dependency on the observations, and it will only have an exponential dependency in the number of actions. Okay, so what are these scenarios? So intuitively, we came up with this, that we want to think about uncertainty as all possible scenarios of the future. And our intuition is that maybe we can make reasonable decisions only considering a set of representative scenarios instead of thinking of all the possible scenarios. So if you think about this, humans do decision making quite similarly. So maybe like a less capable person would only consider one single scenario of the future and make all the decisions based on that single scenario. Maybe a smarter person would have a backup plan, so you would have like 2 or 3 scenarios of the future and make your decision based on those. But you definitely don't consider all possible scenarios of the future that you make decisions. We're going to do the same thing here. Now formally, we define the scenario just by a sequence of random numbers. And we use this sequence of random numbers to define a subtree of this belief tree. We start by sampling one state from the initial belief. Then we take all action branches. Then we take only a single observation branch that we can sample from the observation function corresponding to the next random number in the sequence. So we can continue this, and you can either see that this is like a subtree of the full belief tree. It corresponds to one scenario of the future. Even another sequence of random numbers, we can do this, and it will generate another subtree. We can do this k times. We get k scenarios. We get k subtrees, and we can just merge all of these into a single subtree. Now, this subtree we call the determinized partially observable tree, or DESPOT. This is also the name of our algorithm. So, what we are going to do now is that we are just going to derive a policy from this subtree instead of the full tree. The size of this tree is a lot smaller, as I just told you before. This is only a constant rather than exponential number of observations. So now you only have to do search in this tree, which is not very difficult to code. So if you can code up A star in 1 day, then you can code this whole thing up in 2 days for sure. Okay, I actually don't have to do that because we have an open source software tool that you can just use. I guess one thing before we move on, one interesting question that you may ask is that how well we can approximate the optimal policy just from this approximate tree. So if we think of this as just an approximate tree of the full belief tree, then we can derive some regret bound that is basically a probably approximately correct style regret bound on the value of the policy derived from the DESPOT compared to the optimal one. So this basically tells us that the approximation error is small with high probability. Okay, so in here you don't have to understand the whole equation, but what you can look at is this is the approximation error. And what is important to see here is that it scales well with most of the parameters, such as actions and observations. It's only logarithmic. There are 2 linear terms here. So one is the k. K is the number of scenarios. So this basically says that we can trade off computational complexity and approximation error by sampling more scenarios. And then we have another term. This is the representation size of the optimal policy that we are trying to approximate. This basically says that there's no free lunch. So if the optimal policy is simple enough, that we can hope that we can find this optimal policy or a near-optimal policy in reasonable time. However, if the optimal policy itself is complex, that you cannot escape the complexity being involved in the policy itself. All right. So this is all about the ID. Any questions so far? If not, then I will move on to the APPL toolkit. So this is a C++ implementation of 3 of these algorithms that is available online. You can, there's a link to it, but you can also just Google APPL toolkit. Please don't just Google APPL, because all you will get is stock prices of Apple. So yeah, so just the APPL toolkit or APPL POMDP will get you to on our website. So this software package includes the 3 algorithms. So these are the offline solvers that are earlier work. So SARSOP you have heard about. These are quite often in the other earlier presentations. It is an offline solver. It's restricted to discrete states and observations. But this is the most mature code. So people have been using this extensively. Then we have MCVI that extends this to continuous states and observations. And finally, we have an online planning algorithm DESPOT that I just talked about earlier that can handle both discrete and continuous problems. And this is the one that can scale to very large quantities. So we just recently released a new version of DESPOT that has an improved documentation. And also on our website, we have tutorials for each of these algorithms that are quite detailed. We have also several examples for different benchmark problems that you can start off for your own. All right. So if you want to use DESPOT, you have 2 ways. One is to define your problem. So one is just defining it in an explicit way. This POMDP file is an XML template. It's very easy to define your problems. You just have to name what are your states, what are possible values of your states, what are your actions. So it's basically like a table representation of the problem. Okay, so this is fairly easy. You can do it quite fast for like a small enough problem. Then you also have a generative model, which I'm using the generative the same way as you did earlier. So what I mean is that you have a C++ API, and you just have to implement some of these functions that basically sample from the transition model or observation model. So these are all the functions that you have to implement. So this C++ model has several advantages. Firstly, you can integrate this whole thing into your existing system. But even more importantly, this requires just a black box simulator. So basically, you don't have to represent the whole problem really very large. It's not very practical to represent it, or even possible to represent it in a table format. So this one just generates values, let's say like states, the observation, given a random number. So yeah, and you can also improve the performance of the search in several ways. So this, like, depending on your domain, you may implement your own belief representation. There can be any representation of your belief that is most efficient for your domain. Or you can also implement custom bounds. So it's basically heuristics that guide the search of DESPOT. These are optional, so that you can just get it running quite easily just by implementing these functions. All right. Okay, now I just wanted to show you some achievements and adoptions of the APPL. So this figure compares the offline solvers and how they evolved over time, and these bars show the inverse of the time required to solve a relatively small benchmark problem at tag with 870 states. So in 2003, with PBBI, the first breakthrough in POMDP solving, it still required about 2 days to compute a reasonable solution to this problem. So So by today, or by 2008, SARSOP, our algorithm can do this in 6 seconds. So, but SARSOP still couldn't schedule very large problems. What made it possible was the online POMDP algorithm. So this table here is numbers to show like rewards, expected rewards that different algorithms show that different algorithms achieve on different domains. So there are different problems with increasing complexity. So the first algorithm is SARSOP that is from the previous time. This is supposed to give you a near-optimal solution. Then the other rest is like online algorithms. So you can see that DESPOT does a best in this all these problems. Also, its performance is not so far from POMDP. POMCP is a singular sampling-based approach, but their worst-case performance is a lot worse than DESPOT, and also they have no bounds of the performance. So, okay, the different problems here that I show, some of them you can see has 10 to the power 6 observations. This one, rock sample, has 10 to the power 6 states. And finally, this Pokemon has 10 to the power 56 states and 1,000 observations, so a very complex problem. This is actually a partially observable version of the Pac-Man, this computer game. So here, the difference is that you only get to see a section of the screen, a small part of the screen. So you basically don't know where ghosts are. Okay. Yes, we also applied the DESPOT to real-time robot control task of navigation among pedestrians. So the main uncertainty in this task comes from the unknown intention of the people around. So the robot, this one, is like driving autonomously. It cannot be too careful. So whenever it sees a person, it will stop. It never makes progress. So it has to act a balance uncertainty. In this example, you can see that it's approaching that person. Initially, it doesn't know whether it's going to continue walking, but after some time, it integrates its observations and it's certain enough so that it can proceed. Yes, you can also see this. Someone is trying to block its way. Also, the kids enjoy riding this vehicle. All right. Okay, so these are some applications of the APPL by us and by other people. So it was used for some robot grasping tasks. It was also used for autonomous aircraft collision avoidance. That was actually a collaboration with Michael. This one is the autonomous driving in the crowd, and this is like an intelligent operating system. Some examples that people here in APPL. Okay, we also won some awards. So this includes International Probabilistic Planning Competition 2011 and 14, and
in Riddle. Those are the two competitions that are in.
Yes.
And I should also point out that Riddle does translate to POMDPX, which is right in. So Nandy does have that.
Yes, that's right. You can translate that. Okay, another one is a D-mining competition and ITRA. So finally, I just wanted to spend one more minute on next steps. So one direction that we are working on is addressing problems with rare but critical events. So these are very difficult to analyze problems. That, for example, that this car is driving straight, and you have this pedestrian here. Most likely, it's going to continue walking forward, but with some very small probability, it may step right in front of the car. So this event is not very likely, but it's very critical. This is very difficult to capture for POMDP solvers. So one way that we address this is that we introduce importance sampling to DESPOT. This is IS-DESPOT. We published this recently at a paper. It's not yet integrated into our DESPOT code, but we are planning to do that soon. Another direction that we are working in combines planning, POMDP planning with machine learning. So our recent, so that you could see that the advancement in POMDP solvers great in the last couple of years. But constructing the POMDP models themselves remains difficult. So one recent submission is actually my project, is a POMDP net. So this is a recurrent policy network that embeds both a POMDP model and an algorithm, a planner, that solves this model in a single neural network. Now the advantage of this is that you can train this neural network end-to-end, which means that you can learn a latent model that is most effective given the approximate planner that you have. Alright. This is all I wanted to say. Thanks for your attention. I'm happy to take questions. Yeah.
Is there a plan to put APPL up on GitHub?
It is on GitHub. Maybe not all of DESPOT is definitely on GitHub.
Okay.
And APPL, I'm not sure about SARSO.
It's on GitHub. It's on GitHub. Officially, because I think someone outside of your lab stuck it up on GitHub.
Yeah, I think the SARSOP is not by us, but the DESPOT is definitely. We recently made it like public and linked to our website. Previously it was there, but it was not linked. So now you can definitely pick up on GitHub.